So let's start today's class. Today I'm going to introduce you about the two very important laws, which is known as Kirchhoff's voltage law and Kirchhoff's current law. Okay, so these are the two laws which is extensively used along with Ohm's law for circuit analysis. So let's first try and understand what a node is, what a branch is, and what a loop is. So the definition goes like this: a point through which a circuit element is connected to the circuit is called a node. Okay, so a node is a point where terminal of two or more circuit elements are connected. So if you see here, this is a node. Okay, the left, because there is a voltage source connected there, there is a resistance, so two or more circuit elements have been connected there, so that's why that becomes a node. Whereas these 3 points, if you see out here, okay, there are no circuit elements there connected in between them. A mere wiring doesn't constitute a node. Okay, so if it is just these three junctions are connected by wires, but they don't they can be considered as a single node. They should not be considered as a different node, because there's no potential difference between those 2 points, right? Okay, so potential difference is not the only reason. I'm telling you, there has to be a discrete element which is to be circuit element has to be there between those points. So these are to be considered as a single node. Similarly, in the bottom also there are 4 nodes, but they are to be connected, 4 junctions you can call them, but they are to be considered as a single node. So this is what the standard definition of a node would be, right? Because why we are clarifying these issues are because we are going to use this terminology node when we study about KCL and KVL. Similarly, the next definition which we are going to look at is branches. So the branch of an electric circuit may be defined more precisely as a portion of the circuit between two nodes which can deliver or absorb energy. See, this is important. So whether it can deliver or absorb energy, right? So as per this definition, the short circuit between two nodes are not referred as branch of a circuit, right? So if you see here, these two junctions are connected with an plain wire. So it is so there can't be any energy absorbed there, right, or dissipated, or so that is the reason it's not a branch. So for any two connection between two nodes to be called as a branch, there has to be a circuit element in between. It could be a resistor. All these things which is shown here, they are all any of those elements can be part of that connection between those two nodes for it to be called as a branch. Okay, so this becomes a branch. Okay, so this becomes a branch, and voltage sources, current sources, resistors, capacitors, inductors, all of them, dependent source, independent source, all of them become when they get connected between two nodes, those two nodes along with that element together, they'll be called as a branch. The third definition is going to be a simple one, which is known as a loop. So here if you see, an electric circuit has number of nodes. If one starts from one node and after going through a set of nodes returns to the same starting node without crossing of an intermediate node twice, right, then he has traveled through one loop of a circuit. Okay, so a loop is basically you start from one node and you come back to that node, covering a few branches, but no node should be covered twice. Like a figure of 8, you can't make a figure of 8, so that is a figure of 8 is to be considered as two different loops, right, because they're crossing, that node is being one of the middle nodes is being crossed twice. So those kind of things. So in this particular circuit, you will see there are one is the outer loop, there is an inner loop, there is an in between, there is one loop, in the corner there is one loop, then there is a super loop consisting of two loops. So they're all different kinds of loops. Okay, only thing is there can't be any node cannot be covered twice. So that is the only definition of a loop. Kirchhoff came up with these the two laws, which are because only the Ohm's law is not sufficient enough to solve complex circuits. Okay, Ohm's law can be used only for very rudimentary circuits. You can analyze using Ohm's law. So Kirchhoff came up with these two laws, which is very powerful, and with most of the circuits at low frequencies can be solved using Kirchhoff's two laws and Ohm's law. Okay, all the three laws will be required at low frequencies. I'll discuss why I am telling it at low frequency subsequently, but remember this. Okay, the first law is known as the Kirchhoff's current law. Okay, now it says the algebraic sum of currents entering a node, okay, is 0. Like this is a node, so so whatever current enters, that has to come out. Okay, so this is based on law of conservation of charge. Okay, law of conservation of charge means you cannot just in a single point, you cannot accumulate charge just like that. Okay, so charges can be accumulated only like in a capacitor or some, but just where mere conductors are connected like this, you are pumping in some charge, so that whatever charge is flowing into that junction has to come out. That's why the total algebraic sum of currents has to be 0. So in this case, if you see in this diagram, I1, I2, I3 are the currents which are entering into the node, and I4 and I5 are leaving the node. So I1 plus I2 plus I3 is equal to I4 plus I5. This is what the KCL says. Okay, so it is based on, you got to remember this, it's based on law of conservation of charge. Okay, so here there is one more example out here. Here if you see I1 is entering, so one way of writing it is just try to put on the left hand side the charges which are the currents which are flowing into the junction and which is coming out of the junction on the right hand side. The other option is follow an sign thing, that all entering currents you positive and the currents which are leaving as negative. So you write I1 as positive here, and then I2 it's leaving as negative, then I3 it's leaving negative, I4 is entering its positive, and I5 is entering its positive, and then you equate it to 0. So both these kind of things you can follow. So this is one convention, this is the other convention. Generally the currents which is flowing into the junction is called as positive. Okay, and the current flowing away from the junction is called as negative, right? So if I go these also, if the current is flowing into the source, it is negative. So that is the reason if you say if the current is flowing here negative, it is negative because then the power is being consumed by the source. If it is coming out of this source, it is generally taken positive. So we follow that kind of convention, so that it is giving out power. Okay. So that's how this convention, you can follow whatever convention is suitable to you. Only thing is you have to be consistent. You will get the same answers, you just have to be consistent with whatever you are following for each node. Okay. So that is about KCL. Now if I have to KVL, it is based on conservation of energy. So conservation of energy says the energy cannot be created or destroyed, right? So it is only a transformation of energy from one form to other, right? A electrical generator, what it does, it consumes fuel, it burns it, and then that heat energy is converted into mechanical energy, and that mechanical energy drives a generator, which is again converted to electrical energy. Similarly, you have a battery where the chemical energy is converted into electrical energy, so on. So it says energy cannot be created nor destroyed. It is just you have to change from one form to other. That's it, right? So in an electrical circuit, and here we are not talking in terms of changing the type of energy, but we are telling that if energy is dissipated in the circuit, then energy has to be consumed from somewhere. Okay, you cannot have just one loop where energy is getting dissipated everywhere in the whole circuit, that the energy is getting dissipated and there is no element in the circuit which is not giving that energy. Okay, so that is what based on law of conservation of energy. Okay, but in a particular loop, it is possible that they are all dissipating. But if you take the whole circuit as a full, then there has to be someone who is giving that energy. Like if the current is flowing through 4 resistors like this, I square R heat will be generated. But somewhere in the circuit, there has to be some power supply source like a battery source or a current source or a voltage source which is giving that energy. So overall there has to be conservation of energy. Okay, that is the concept. So here KVL says that the algebraic sum of voltages around a closed path is 0. So if you take a closed path, we have defined what a loop is. So in a loop, the algebraic sum of all the voltages have to be 0. So if I take this convention as positive on the left hand side and negative on the right hand side, then V1 plus V2 plus V3 plus V4, that has to be 0. So this is what the KVL says. Okay, so this is another very important rule which we need to remember. Right, now there are certain limitations of KCL and KVL. Okay, so if you see at 1 megahertz frequency, so generally at home we are working at an 50 hertz, so that is even lesser. So I have just started with 1 megahertz. So the wavelength corresponding is 300 meters. So if I give 1 megahertz signal out here, I can assume that the same current is flowing in a circuit when I have an RLC, because right, the same magnitude of current would be available in this loop. Okay, but when I come to high frequencies, say 1 gigahertz, or if I go to further high at 10 gigahertz, okay, the wavelength is 3 centimeters, right? So it is possible that the resistor itself is 3 centimeters, right? So when I am powering it up with say some 10 gigahertz signal, right? So there will be a current flowing in a sinusoidal manner. So at any given instance, the magnitude of the current in R, L, C may not be the same, right, at 10 gigahertz, because you see the wavelength itself is so small, 3 centimeter, and this circuit physically, when we realize, may take more than 3 centimeters. So you will find that the magnitude of the current is not same in all these three. So our KCL and KVL fails here, and more so at these frequencies there will be radiation of power also. So a resistor may not have only I square R power, it might also radiate some power. That is same true with the with these wires and transmission lines and things like that. So that is why KVL and KCL is only applicable at low frequencies. Is this aspect clear to all of you? Anybody?
Yes, sir.
Yeah.
So can you explain it once again a bit about the change in or the power radiated part?
Yeah. Okay. Yeah. Sure. See, when I'm talking about a signal at 1 megahertz, suppose, right? So the wavelength corresponding, how do we find out the wavelength? It is velocity divided by frequency. That is the formula for obtaining the wavelength, right? So 1 megahertz velocity of this will be 3 into 10 to the power of 8, right, meter per second, divided by 1 megahertz, so it will give around 300 meters, right? So that at 1 megahertz the wavelength is 300 meters, right? So if it is 300 meters, when I connect R, L, C like this for a circuit, okay, R will be what 3 centimeter, L will be say another 2-3 centimeters, capacitor will be less than a centimeter. So you can assume that this IT, which what we have used for KCL and KVL, this IT, it is same at any given instance. Although it's an AC signal, with respect to time it is changing, but if I take a snapshot, pause the signal for a minute, the same current is flowing through all these in this circuit, right? Isn't it? Satakshi, am I clear?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
But when I am talking about a 10 gigahertz signal, right, the wavelength is 3 centimeter, right? So that means the 3 centimeter within few nanoseconds, every 3 centimeter, right, the amplitude of the signal will change. Right, it's an oscillating current which is going here. So because now if you see these components are size of the components are comparable with that of the magnitude of the wavelength. So the same at any given instance, the current magnitude will not be same across all these components. Is it okay?
Yes, sir. Correct.
Yeah, yeah. Okay. So, this premise of V into I will remain constant in this loop, and all those things will fail here. So, KCL KVL will not be used for these high frequency. So, whenever we say high frequency, so whatever we have these small softwares like LT Spice. Or for that matter cadence and things like that, when we work on these softwares, most of them they use the KCL KVL and electric, the background is an electric, whereas when we are speaking at a gigahertz frequency range, then we have to the solvers have to take into consideration the electromagnetic fields there, so the things get radiated. So it's not the KVL KCL. Apart from that, over and above these, those electromagnetic equations also will come into picture. Right, so it is most likely in that case, and all the physical dimensions also have to be taken care of. So it is not an pure and simple manual calculation using KCL KVL will not hold good. Okay, so that is the reason, that is the limitation of KCL and KVL. Right, so so these are the three basic laws which we are Ohm's law, which gives V is equal to IR, KCL, which says summation of current into a node is 0, and KVL, which says the summation of voltage across a loop is equal to 0. So these are the three laws which generally we are going to use to solve equations. Okay. This I mentioned in my last class that the sum of three resistors in series is going to be R1 R2. When they are connected in series, the net resistance will be R1 R2 R1 plus R2 plus R3. Okay, so this is kind of an proof of that using the KVL. So if I write the KVL, total voltage V is equal to V1 plus V2 plus V3. This equation comes from the KIRCHHOFF'S voltage law, right? And we also know that V1 is equal to I1 R1, V2 is equal to okay, this has gone into suffix R also. That shouldn't have been the case. It is an I into R1, I into R2, and I into R3. Right. So if you sum it up, you will get V1 plus V2 is I R1 plus I R2 plus I R3, and then we take I common here, and then we substitute this as an R. If we call it as an equivalent resistance, we put an IR, so you get R is equal to R1 plus R2 plus R3. Okay, so this is a common thing which we all know. So this we can this is just an proof of this that a series resistance is sum of the resistance using the KVL. So this way we can prove it. Similarly, resistors in parallel. So this also we are aware of this equation. 1 by R total is 1 by R1 plus 1 by R2 plus 1 by R3 plus. So that proof also we can do using KCL, in fact. So you know different currents are flowing here. This is the total current which is coming here. So I write the total current is equal to summation of all the currents. This is the KCL. Now replacing each of these currents, now the voltage across all these resistance will be the same. In this case, the current going through all these resistances were same, whereas in this case the voltage across these resistances are going to be same. So I put V by R1, V by R2, V by R3, V by Rn, and then substitute each of them by I1, I2, I3, and just remove the V component. So you get 1 by R total, you will get this equation, right? So this is a simplified expression of two resistors in parallel, which is R1 R2 divided by R1 plus R2. Okay, by intuition, you should know that when you have connecting two resistances in parallel, the new resistance which would become will be lesser than the lowest of the value. Okay, many a times in multiple choices, say I am writing say 10k parallel to 8k, right? And if there are 4 options, out of which 3 options are greater than 8k, so don't waste time trying to compute the parallel resistance. You should know that when there if 10k and 8k are in parallel, the net effective resistance is going to be lesser than 8k, because you already single 8k is offering some kind of resistance, so you have put even 1 mega ohm in parallel to it, right? But then there is some path available other than 8k for the current to flow, so the net resistance has to be less than 8k, right? You have an 8k and it could be tera ohm also, but it will still, the net effective resistance will be less than 8k, because there is an alternative path available. So in such cases, please don't use your calculator and waste time, okay, when you are attempting such questions. Okay, so that's about resistors in parallel. Right, now this equation should be very handy. You should try to remember this, otherwise you will waste lot of time. This is known as voltage division. So if you have a voltage supply which is V applied across two resistances R1 and R2, then the voltage across R1 will be R1 into V divided by R1 plus R2. Okay, this also comes from a simple Ohm's law itself, because the current will be same, which will be given by V divided by R1 by R2, and the voltage across R1 will be into R1. So this is known as the voltage division. So similarly, voltage across V2 will be R2 divided by R1 plus R2, right? So the current will remain same. If higher resistance means higher voltage. Okay, so R1 comes in the numerator. So you got to remember that way. See, in the voltage denominator is R1 plus R2, and since we are talking about the voltage out here across this resistance, the same current is going to flow in both these resistance. So higher the resistance, higher the voltage across that particular resistance, right? So you have R1 the numerator. So V1 is R1 divided by R1 plus R2 into V. Similarly, V2 is given by R2 divided by R1. So this is voltage division rule, which you should remember. That will save time when we are solving problems, right? Similarly, you have something known as current division. If I say the current, if this total net resistances in parallel to Rx, if I call that RT, then the current going in Ix will be RT divided by Rx plus RT into IT. So IT is the current which is coming here. Now if you see, it is this RT, okay, not this Rx in the numerator. Okay, again you have to why it's coming in the numerator. It's because obviously if you are putting more resistance here, the current will find it easier to flow into the resistance which we are interested in, right? So here it came in the numerator, because if it is higher, more voltage is going to get dropped here. Here if this is higher, more current will try and flow into the rest of the branch, right? So that is why we are more interested in the resistance here, which is not part of our desired path. Okay, so that this rule also it's very handy, so you need to remember this. So I1 is R2 divided by R1 plus R2, and I2, the current going from here, is R1 divided by R1 plus R2 into IT. Okay, so the more current will flow here if this resistance is high. Similarly, if R2 is high, more current will flow into R1. So that is the change with regards to the voltage division rule. So these are two things which you need to remember. Right? Okay. So before we call it off today, let me just show you these things. This is KIRCHHOFF'S voltage law. So you see, I have applied around 100 volt out here. And there are two resistance 50 ohms 50 ohms which are connected in series. Now if you see, this is the 100 volts, this is the source voltage. So you will have 50 ohms and 50 ohms distributed across these two resistors. Okay, so I put two voltmeters out here. So you see 100 volt. So this is law of conservation of energy, or the net voltage in a loop is 0. 100 volt and then 50 50. Okay, so this is, so if you take the algebraic sum, it will come to 0. Okay, is it clear to all of you? Right?
Yes, sir.
Yeah. Okay. So if I go to the next one, here if you see, now the ratio of these resistances have been changed. Initially it was 50 50, and now I put a 20 ohm and an 80 ohm. Now if you see the voltage accordingly, higher the resistance, the voltage will be higher. Okay, that is what we learnt about the voltage division rule, right? So 80 ohms, so you have 80 volt now across this resistance, and 20 volt here. Again 80 plus 20 amounts to 100. So again this the total net voltage in the loop is 0 out here. And since we have maintained this 80 ohms and 20 ohms as 100 ohms, like it was 50 50 ohms earlier, now it is 80 plus 20 again comes to be 100. So the current remains at 1 ampere. Okay, so this is how we analyze this circuit. And then here what we have done is, instead of 20 and 80, we scale this resistance by a decade to 200 and 800, and now the current accordingly, so the net resistance as seen by this voltage source, if you see, is 1k. So the current has dropped to 100 milliampere. Okay, but still nevertheless, if you see, the total voltage of 100 volt will be distributed across these two resistors, because the ratio remains same, 8:2. So you have 80 volt and 20 volt. Okay, the current has changed, but the Kirchhoff's voltage law holds good in this circuit. Okay, is it okay? Okay. So let me move to the last circuit one more. Yeah, here we have now multiple loops in this. Here you see, this is 20, and there is an 160 ohm out here. So inside this there is one loop. So if I move across in this loop also, you see 20 volt here and 80 volt here. So this is 100 again. So the KVL holds good here. Now if I see this outer loop, I have a 20 volt out here, and then 40 volt here and 40 volt here. So 20 plus 40 plus 40, again 100. So you see, whichever loop I take, if I take this loop, this internal loop out here, this is 80, not here top here 80. If I see here, this is 40, this is 40. So this 80 has been split into 40 out here. So there are one big loop outside, there are two small loops and one loop out here. So in all these cases, KVL will hold good. And also if you see the KCL part, there's an 1 ampere current which is coming into this node, that is been split into 500 milliampere and 500 milliampere out here. So there is an this is just a voltmeter, right, connected. So for simulation, voltmeters are generally high impedance, so it is an ideal voltmeter will have an infinite impedance, and an ideal ammeter will have zero impedance. Okay, so that can be connected in series, so that you got to remember. But in practical cases, the voltmeters will be in few mega ohms range. Okay, so you got to remember that. Okay, and now here also this 500 amperes is coming into this node, and they're getting summed up into 1 ampere. So you can see how KVL and KCL conditions are met in this circuit. Okay, is this okay with all of you? Okay, so actually today we'll slightly call it off early, so that's all for today. In the next class we will take on some problems of KCL and KVL, and some super nodes and super loops also. So I'll give you certain examples of that, so that and then we'll follow it up again with a set of problems in the tutorials. So next class and the next tutorial, you will be very comfortable with the KVL and KCL aspect of and basic circuit analysis. Okay, thanks a lot for today.